Okay, if you saw the wordless version of this whole thing in 2 videos, then you might well understand what's going on, but let's just review it real quickly. Started with a circle, put a point in the center, drew a y-axis and an x-axis, then marked what were supposed to be equally spaced points around the circle. Did fairly well up to here, and it's kind of deteriorated as we went around, but enough to give you the idea. Then drew a horizontal axis here, marked off a bunch of equally spaced points here that are going to correspond to the points around our circle. For each point on the circle, we either projected the point over to the y-axis or drew an arrow to represent the value of y corresponding to each x value on the graph. We then paired these arrows up corresponding to the successive points. So each respective point here corresponds to one of the points around here. And having done that, we sketched a curve, and we called that an unscaled sine curve. At that point, we didn't even have a y-axis here. We just had a horizontal axis with points lying above or below the axis, according to whether the points here lie above or below the x-axis. I think I said that right. Points above or below the horizontal axis here, because I'm not calling this an x-axis. There's only one x-axis at this point. That's this one. This horizontal axis, each point will lie above or below that axis, depending on whether the corresponding point over here lies above or below the x-axis. Okay. Then we did something very similar, very analogous, except this time we used the distance of each point to the right or left of the y-axis. So we're talking about essentially the x-coordinate of each one of these points, and that's what's going to determine how far above or below the horizontal axis each point lies. So we start with this vector. We turn it around here because it's going to be represented by a vertical distance above or below the line. So we take this vector, turn it around here, and we do the same with each vector as we move around the circle, and we get this sequence of vectors, and therefore this graph. Okay, now we can scale these axes. Remember, right now we have unscaled curves, and I don't believe I labeled this. This would be, oh yeah, I did, the unscaled cosine curve here, unscaled sine curve here. Okay, well, now we want to scale things. Okay, that means we want to put a scale on the horizontal axis here. Well, the scale on the horizontal axis, one easy way to scale it would be to say, well, let's scale it in terms of numbers of revolutions. So we have one complete revolution between here and here. Well, if this is our 0 point, then 1 would go here. So if we're scaling it in terms of one revolution, which I've written in orange up here, I've written the corresponding scale here on this axis, on this graph, and here on this graph. So the graph goes from 0 to 1. Either of these graphs goes from 0 to 1, and each graph represents a complete circuit around the circle. Okay. Another way of scaling it would be with arc distance. Okay, the arc distance is 2 pi times the radius of the circle, because the arc distance for a complete revolution is 2 pi times the radius, which is the circumference. And if you understand the definition of pi, you understand why that is. It's not just a formula, it's a definition of pi. Okay, pi is the ratio of circumference to diameter. Diameter is twice the radius, therefore distance around the circle is 2 pi times the radius. Okay, well anyhow, so the distance around the circle is 2 pi a, so the complete cycle would be scaled at 2 pi a on the horizontal axis. Okay, another way to do it is in terms of what we call radians. It's just, in this case, 2 pi. Okay, so at this point now theta would be 2 pi, or here theta would be 2 pi. I'm using theta now because this could be an angle. Okay, and of course we could say, okay, well, theta is 360 degrees for a complete revolution, and that's perfectly valid as well. It's a whole lot easier to do your arithmetic and not worry about unit conversions if you use radians for your angle. And incidentally, the radian is the default unit of an angle, so I don't have to write radians on here. If I say theta is something without specifying the units, that means that theta is measured in radians. If I use units, degrees, I better specify the degrees. 360 without the degree on it means 360 radians, no matter what you might intend it to mean. Okay. Now, let's do one more labeling where we assume that a revolution requires 30 seconds. Now, we could use any time for our revolution, but just 30 seconds as an example, and you can adapt that. If it's 0.05 seconds, you could adapt it to that. If it's 48 years, you could adapt it to that. Okay, but in this case, a revolution is going to take 30 seconds. It's going to take 30 seconds for us to get all the way around the circle. Now, if it takes 30 seconds to get all the way around the circle, then, well, if this is 0, we would label this point as 30 seconds. Okay, and that would work perfectly well for this graph or for this graph. Okay, right there's 30 seconds. And we could even say t equals 30 seconds. I didn't do that. I used theta up here to indicate angle. I could use t to indicate time. And if now this requires 30 seconds, we can get into some very significant interpretations of some of these quantities. So if one revolution takes 30 seconds, that means we're moving at one revolution per 30 seconds, which is 0.033 repeating revolutions per second, or 1/30th of a revolution per second. Okay, that means every second you move 1/30th of a revolution. So you go 30th of a revolution for 1 second and for 2 seconds and so forth. By the time you get to 30 seconds, you're all the way around. That's what that means. And we call that an angular speed, measured in revolutions per second. Another way to do this is in radians per second. Okay, we divide our 2 pi radians, which corresponds to a complete circuit around this circle, and divide that by 30 seconds, and the arithmetic is easy. 2 over 30 is 1 over 15. We end up with pi over 15 radians per second. Or we can rate, that's how we read it, pi over 15 radians per second. It's radians divided by seconds. Or, if we wish, 360 degrees divided by 30 seconds gives us 12 degrees over seconds, 12 degrees per second. This one is easy to visualize. You can visualize 12 degrees a lot better than you can visualize pi over 15 radians, unless you happen to be really accustomed to visualizing multiples of pi in radians. Okay? This is easier to visualize, but this is much easier to do calculations with because the units work out nicely. And I'll illustrate that in a minute. Now, if your radius of your circle, and I've indicated the radius now by this purple arrow and purple label A. If the radius of the circle is A, then several things can happen. One is we can label the vertical axis of our graph. Okay, we can put negative A here and A here. We put negative A here and A here. Okay, the highest this graph can go is A because the biggest Y, or the biggest distance above the axis on this circle is going to be here, where that distance is equal to the radius. And here, of course, you have the same distance, but it's in the negative direction. So the graph is going to go from plus A to negative A. Same with this graph. So we can now label the vertical axis if we know what the radius represents. Okay, now what if the radius represents 5 centimeters? So if A is 5 centimeters, then, well, let's see. This quantity, if A is 5 centimeters, then the distance we have to move around the circle is 2 pi times 5 centimeters. So we would have another angular velocity, and I don't think I indicated here that this was an angular velocity, or an angular speed in this case, not being too picky about distinguishing velocity from speed at this point. But see, we have an angular speed of pi over 3 centimeters per second. That works out because we take the angular the distance that we travel around the arc, 2 pi a divided by 30 seconds, and we do the arithmetic and see if that comes out pi over 3 centimeters per second. Okay, that's an angular speed. And that's what we call, it's not an angular speed, and matter of fact, I just circled that as an angular speed, and that was ignorant. It's not an angular speed, so got to get rid of that line, and we got to get rid of that circle. I'm not going to do that. I said that was an angular speed, and it's not. It's the speed along the arc. It's how fast we have to move if we're running along this arc or walking or crawling along this arc to get around it in 30 seconds. The distance around is 2 pi a, which is 2 pi times 5 centimeters. Takes 30 seconds. We divide the distance by the 30 seconds, and we get pi over 3 centimeters per second. I'm busy explaining, and I wasn't thinking there. Anyhow, that's a speed along the arc, not an angular speed. So ignore that arrow and ignore that circle there. Okay, now here's a big deal. Okay, and this is explanatory of a lot of things that are very confusing to a lot of students when we talk about this kind of a model and this kind of a situation. If we multiply pi over 15 radians per second, which is an angular speed, by the 5 centimeter radius, what do we get? We get pi times 5 divided by 15. Pi times 5 divided by 15. 5 divided by 15 is 1/3, so we get pi over 3. And pi over 3 what? Well, it's pi over 3 centimeters per second. For reasons that might not be completely clear to you, it goes back to the definition of a radian, which I've kind of talked about. I haven't talked about. I've used it implicitly. We talk about it more explicitly. If you're seeing this, you should have already seen the definition of a radian, and hopefully you would know the definition, but it's kind of a tough thing to get your head around, so not everybody that's seen it really understands it. The idea is simple enough. A radian of angle is the angle for which the distance along the arc is equal to the radius of the circle. So when we multiply a radian of angle by the radius of the circle, we get just the unit of the radius. Okay. Now I'm not going to belabor that point. This is an overview, but we see that the result that we get when we multiply the angular speed by the radius is our speed along the arc, how fast we got to crawl or run or jump or whatever to move along the arc and get around it in 30 seconds. One more quick connection. If we do a tangent line at the point where the graph is steepest, which would be here or here or here. Okay, now we have a negative slope here and a positive slope here, but the steepness is the same. If you're sliding down this or sliding down this, you're going to slide down just as fast. Okay, so now if A is 5 centimeters, in the first place we can relabel the graph. Instead of just negative A and A, we can have negative 5 centimeters and 5 centimeters here and here. If A is 5 centimeters, then the magnitude of the tangent line slope, and I should have said the magnitude of the maximum tangent line slope, is going to be pi over 3 centimeters per second, in agreement with the angular speed around the arc. Now the reasons for that, I've got to take a little bit of analysis and a little bit of understanding. If you understand how to interpret graphs and think a little bit about it, you can probably figure it out. But that's just another really important connection. And the slopes of this graph do represent speeds. And in this case, where A represents 5 centimeters of distance, and we then have this connection with the speed along the arc. Maximum speed here is going to equal the speed along the arc.